not that you're just stripping off one layer and then adding another layer. There has to be some other things that go into it, right? So like, let's say you're on Wi-Fi here, and then you're gonna go to Ethernet, and then you're gonna go out something else, like cable modem. And so you're on your laptop, right? And your laptop has a transport protocol. We're gonna just start with something super simple. It's gonna send a UDP packet out to resolve an address. We'll discuss later when we get to transport protocols that the DNS often uses UDP. So there's a TCP version of DNS also. It uses UDP to go out. So in the upper application stack, right, the DNS service constructs a UDP packet. Constructs a UDP packet, and then it passes it down to the network protocol. And in this case, that's IP. And then IP gets passed down to the data link protocol. And in this case, that's 802.11, right? And then that gets passed down to the physical. And then it gets broadcast out in the air because 802.11 is over the air, right? So this actually goes out over the air, right, and it gets to the network access point. So what happens here? Well, that network access point is a device that has both Ethernet and Wi-Fi built into it. It has both of them. And so it receives this on the physical layer, and this is the air, right? And then it goes up to 802.11, and then it goes up to IP. And inside the same box, now it goes down to Ethernet, right, and down to physical. And then it goes out to physical, and let's say over actual wire to Ethernet, and then the cable modem actually has Ethernet and the cable modem part of it built in, right? So it goes into physical, Ethernet, IP. Now notice that it looks like the IP is being is just being passed over. So, and then it goes back into IP. And then this time, let's just call this cable modem. And then out the physical. And then physical for cable modem, that would be like a coax wire. Right? And then off. And then it goes into the internet, and then at every different transition from one different data link layer device to another data link device, this happens over and over and over again so that it gets through the Ethernet. So even if 16 hops later we come out and we're on Wi-Fi again, right? It is transferred one into the other. And so while this seems not so bad, right? All we're doing is we have a device that kind of sits on both sides, and it goes down, and we have 802.11, right? So it's just a radio, and then we're like, oh, it needs to go to Ethernet, so we need to build a data link layer for Ethernet. But it's not actually that simple. The problem is we went through all this time talking about the data link layer, and that the data link layer, you likely are engineering the size of the packets. Well, what happens if you go through the internet and now you have a Wi-Fi packet that is 2,000 bytes, and it goes to Ethernet. What's the packet size in Ethernet? It's 1,500 bytes. Well, you can't magically stick 2,000 bytes into 1,500 bytes. You might be able to contrive some compression that sometimes would work, right? But let's just say that it's has high entropy, and that there's just no way. You can't compress it. So what do we have to do? We're gonna have to split it, right? If we want to send that actual packet, we're gonna have to split it, right? So now, if we're splitting it, now we're going to have 2 packets that we're going to have to put on here. And we're going to have to figure out, and because the original device that sent the packet didn't know that it was going to be split, we're going to have to figure out on the other end some kind of mechanism in here to reassemble those in the order, in right order. So this isn't TCP's job, or UDP's job to figure this out, right? Because UDP sent this guy sent a packet out, and he expected it to get through the network. Now later on, we'll discover that it might be better to come up with a mechanism to just figure out the right size for your packet before you send it. And we'll figure out how to do that. Because this actually puts a lot of burden on all of these devices. So these devices have to work very quickly, right? Because we're trying to send them through the ether, to the internet, and we expect some kind of relatively fast response, particularly if the data is time sensitive. Right? If this was slow, then VoIP over the internet would never work. It has to be fast. So, but this puts quite a load on all the devices. In addition to that, there may be some other strange network devices that we're likely, some of us are unfamiliar with in the middle of the internet. So, what we're talking about here is we're talking about moving one packet to the other side, and that's the datagram model. So the datagram model is we are going to send packets across the network, and the packets can find, they have an address in it from IP, and they can find their way through the network and arrive at the other side. This is much akin to like the traditional post office. You wrap your packet up in an envelope or your letter up in an envelope and you mail it. You don't understand actually how it gets there, you just mail it and it arrives most of the time. There's other things inside of the internet and other networks that are more of a virtual circuit model. Virtual circuit model is much akin to like a telephone line, right? You call somebody and you establish a communication with them, and then the packets or data is carried across that line without addressing, at least without IP addressing. So let's talk about those models a little bit first. So we're going to have A talk to F. And so we have this interconnected network, and we're going to send out our packet. And we're going to send it out, and it's going to go through this process at every point that it arrives at, of stripping off the physical layer and the data link layer information, replacing it because this device has both, and it will rebuild it and forward it on. But the IP stays intact, except for when it divides up, right? So let's say that it goes through this path here. This can actually be achieved because the IP header information has the address of F in it. So we haven't talked about building these tables yet, which is routing, but let's imagine what the tables look like inside of C and E. So C and E has a table, and for right now, let's just say that it has a table for F, and the table in here is E. So this is destination, and this is out. So a packet arrives that's addressed to F, it knows to forward it to E. It doesn't actually know how to arrive at F. It just knows that E knows the next hop. And then E actually knows F. A's table would look like this, right? So let's say there's a host out here. So host 1 sends 1 to F into router A. Then A knows the next hop is C. And that's all of the individual routers know. This is not like the data link layer. Remember, the data link layer knew where everyone was. It kept a table of every endpoint. But because, as we discuss IP and learn about IP addressing, IP has hierarchies. And so since IP has hierarchies, you can divide it into next hops. And the router tables can be much smaller because they only need to know what the next hop is. Now, A could change sometime for whatever reason and say, hey, the next route is B. And of course, B would have a table for F, and let's say that it just forwards it back to C. Right, and so long as that all the tables were intact, we would find a route to the next one, even if A's table changes. And we will talk in depth on how those tables are calculated and changed. But this is a datagram model, right? It relies on the IP addressing of the packet to come in and read that IP address and look up in a table and do the forwarding to the next device. So, and all of these are a store and forward approach. So the packet, sometimes for a very, very short time, is always stored in the device. So, and in reality, it is often changed. The packet is changed because we're moving from one data link layer to another data link layer. So if that is the case, then the packet is being stripped off. Now we're drawing them like this, but the packet in reality looks like this. So we have this UDP packet that we started out with. This is our data, right? And then IP gets appended on it. And then in this case, 802.11 gets appended on it. And it also has a trailer. And then the physical layer is just the physical stuff, right? So it doesn't actually change the packet. So, but the packet's actually being changed every time it moves from one to the other. And it gets sent through the network in this direction. But that is the datagram model. There is a virtual circuit model. A virtual circuit model kind of breaks this paradigm in that you might have this C. So in that datagram model, we have this router C right here. But inside of C might not be a single device. It might be two devices. Those devices might be very far apart from each other. So think of it like when you send a datagram packet out and it goes up to Denver to a core router. And that core router wants to send something over a fiber line over point-to-point protocol to another core router in New York. So those devices might actually look like one device from your perspective. And what happens is your packet arrives here. So by the time, let's say it arrives over Ethernet. And then you had like this UDP thing. So it arrives over Ethernet with the UDP data packet in it. And C has a virtual circuit. C sub 1 has a virtual circuit, and actually has many virtual circuits to C sub 2. So in the case of, not in all cases for all virtual circuits, but in the case of like the core router, like using MPLS inside of the internet, right? You set these things up beforehand, but there is some kind of setup. You say, hey, there is a device in New York, it's attached to this line, right? And we're going to just forward it through as if it was inside the fabric of the switch itself. And so what happens is, and point-to-point protocol has a packet size of 900, so this thing is definitely getting split up. And so it will split this thing up, transport it over here, and then rebuild it on this side. And it just appears out the other side. This is not a function of IP. There's no addressing out here other than C essentially thinks C sub 2 is a port that is going to forward it out to. And then on the other side, the device happens, it gets reassembled into IP and datagram happens again. And we'll talk more about temporary virtual circuits with TCP with flow control because they look very much the same. But in this, for MPLS at least, it will add like an MPLS on here, which is the data link protocol, or the virtual circuit protocol, and then it has point-to-point protocol here, which is the data link layer. And then these routers, they forward on something entirely different than the address. So where before we had, hey, the IP address is F, and then this one knows we're going to go out to B. We arrive at B, it's F. We know it's going to go out to C. We arrive at C. So it's using the IP information that's inside of the packet. MPLS is actually going to add a virtual circuit. So in that model, it comes in from A. And it is going to assign it a number. We're just going to call that 1. And then it will go across the virtual circuit, and there might be more than C sub 2 and C sub 3, right? And so A1 will come over, and then this one will keep a table. It's like A1. Or actually this would be C sub 1, 1. This is our table. And then it might go out and create C sub 2, let's just call it 7, because it already has other virtual circuits. And those are assigned dynamically. We set up a circuit and it just assigns it a number. And each of the enter points inside of the virtual circuit will only see, instead of reading all the IP information, it will only see where it came from and what circuit number it was. That is in this case in the MPLS header for MPLS itself. And then where to forward it out, which line to push it out on. That's it. It doesn't read the IP information at all. It is this first virtual circuit that decides what trail to go down. Go ahead.
So a traceroute would never see this?
So what you may see is like star, 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 yeah. Right? Because I believe, don't quote me on this, I believe the time to live is still being ticked. So you'll see it like time, like stars, and then time to lives are just being decremented, and then it'll rise out at IP again. And I'll look at that for sure, but I'm not sure that they would even, ICMP would actually even see it go through it. through it because it's not ICMP, it's still IP. So I don't think it would know. But I'm pretty sure that the time to live has to be decremented because you still have some of the same problems of phantom packets living in your network. So imagine a phantom packet was going through this virtual circuit, kept going forever, and there's no time to live being decremented, then you'd run into the same problems. And we'll talk about time to live as we go on. Now inside of each of these devices, and whether it's a virtual circuit or whether it is a datagram model, we drew this last week, right? There's a router. It's just easier to represent it as inputs and outputs, even though they're really in the same ports. So 1, 2, 3. These are inputs. So sub I, and then 1, 2, 3. These are outputs. And we have buffers inside of here, and a fabric. And so when a datagram, because this is a stored forward model, even if it's stored for just a tiny bit, right? When the packet comes in on port 1 here, right, it gets filled in inside of this buffer. And then it goes through the packet, or the switch fabric, and then it gets put into the output buffer, and then the output buffer becomes a queue. The input buffer can be a queue too, but it becomes a queue, and then those packets are put on the output buffer to go out the whatever port as fast as they can. But it has to work this way because you may have 1, 2, and 3 all trying to go out 3. And these are coming in at line speed, and this is the same data link model on both sides. If they're coming in at line speed, now you have 3 times the line speed trying to be pushed out 3. And so there has to be a queue. It works well, even though you're trying to do 3 times line speed, but because computers are often bursty on the other side. So they're not always trying to send packets. You know, they talk for a lot and then they quit talking. And they talk for a lot and then they quit talking. And so since that is happening on the other side, the queuing system works fine on getting most of the packets out. But if the buffer fills up, what happens? Packets get dropped. They're dropped. And then if packets are being dropped, in this model, since we're already in network layer, for IP at least, IP relies on the upper layer transport protocols to decide whether that thing needs to be retransmitted or not. IP is the best effort delivery. If you want reliable delivery, your transport protocol needs to do that. That is not necessarily the case for virtual circuits. Virtual circuits might be guaranteed delivery. And I can't remember if MPLS itself is guaranteed or not, but likely it is because the way it works is kind of like an internal switch, right? So there are other protocols other than IP at the network layer that have guaranteed delivery. So, why would we need virtual circuits or datagrams? Why is there both? What are the pros and cons between both? What's a pro? Give me a pro of the datagram model.
Can handle a changing network.
Can handle a changing network. You are right. It is dynamic. A virtual circuit cannot handle a changing network. So, and by changing network, that doesn't necessarily mean like we are going to consciously make a change, or it might be that something just dies in the network. So if you had a virtual circuit chain, right, and something dies in the middle, that's not good. Remember, in the datagram model, all you needed to know was the next router, right? And then if that router dies, when we get into routing, you'll see that the routing tables will actually have a number of different routes, and it will choose the best route based on your specifications, right? So if one of them dies, then we could simply send it to the next one. In a virtual circuit, because each router is individually storing the next forward information, and that is dynamically created, it has nothing to do with IP addressing at all, then if one of them dies in the middle, the whole circuit dies. And basically you have to reestablish a circuit at some other end. So one of the pros is datagram model. Give me a pro for virtual circuits.
You can stand them up quick.
Routing is still faster than doing a virtual circuit as far as stand-up. I said that virtual circuits can have guaranteed delivery, right? So guaranteed delivery is a part of quality of service, right? So virtual circuits have it much easier because IP basically works on the lowest common denominator. So if you have a quality of service guarantee in, like let's say you have a network over here that has a quality service guarantee, and even the same quality service on this side, but it has to route through the internet, your quality service might not make it. Because IP has to, for quality service, it can't really be added well. And so even though there's some quality service built into IP, it's very minimal. And so it's the lowest common denominator. So it ends up being, your quality service is always the weakest link in the chain. And if you go through 15 hops through the internet, it was the weakest quality service becomes your quality service. Where virtual circuits, because you're adding a circuit and you're constructing it at that time to deliver packets from one side to the other, you can use that construction process to pick your quality of service. Well, I'm going to go from C sub 1 to C sub 3 rather than 2 because C sub 3 has better quality service. It meets my requirements. And I can pick my virtual circuits that way. What else? Anything else?
Does it have a faster transit time for virtual circuits?
Yes. Almost always has a fact. And that has something to do with quality of service, but it also has to do with the addressing. So when you're pulling the addressing in, you're not having to look up, and when we get to the hierarchy for IP, you'll learn that we'll have to look up, divide out, and figure out which is the next port, and there's just some math involved that each router has to do. Where a virtual circuit is just a tiny little label, and that label just goes out of port. It is almost super simple port forwarding. No math involved.
The whole route's dedicated?
Yes, in virtual circuits, yeah, the whole route's dedicated. Now that doesn't mean that it doesn't receive an IP and deliver an IP packet, right? But the whole route in between is dedicated.
Whereas in the other model, datagram is dynamically.
Oh yeah, it could go different
That's
paths, right? So some of the things that it has is virtual circuits have better quality service. They are likely to deliver packets in order without any of the transport layer interfering. Have super short labels to be able to fast forward packets, and they don't have they don't have computation intensive routing tables, right? Because it's really, it looks from the virtual circuits perspective, it kind of looks like the inside of the switch, right? Even though the distances might be great, they kind of act as in concert with each other. But datagrams don't need any setup; they can just be sent on their way. IP is very flexible in the way it's designed for internetworking to just push packets from one network to the other. And if things go bad, it's easier for datagrams to recover. So let's talk about a little bit about IP. We'll be on IP for a while. IP again uses the lowest common denominator protocol, right? So if you have a string of 15 different hops, whatever was the lowest common denominator in whatever you pick, whether that be quality of service or bandwidth, becomes your state. Right, so if you have gigabit Ethernet on this side, gigabit Ethernet on that side, but you have to go somewhere through some other network that has 1 megabit per second, your connection is really 1 megabit per second, right? It doesn't matter. So if you spent all the money to get 150 megabit per second from Comcast, right, but you're connecting to some university network that only provides 10 megabit, then you only get 10. Doesn't matter that you have 150 on your end. So it's the lowest common denominator. But IP allows us to do some things that weren't otherwise possible in our data link layer model. Right? It allows us to be able to translate between different data link models. And why wouldn't we just decide we're going to specify a data link model? We could build a much faster Ethernet or internet if we just decided this is the model. Why wouldn't we do that?
Backwards compatibility.
Backwards compatibility and forwards compatibility, right? So one of the things, if you think about it, IP was a solution to a problem to be able to create internetworking devices and allow networks to, networking technologies to be innovated upon, become faster, better, stronger, however you want to look at it. And because you can do those networks in isolation, right? UCCS can just build a better network, and they don't have to wait for the rest of the internet to build a better network. But ironically, because IP is the solution, IP is also, it itself has the same constraint. It is very difficult to upgrade IP because now you have to get everybody to do it. So for the same reason where they chose to have internetworking rather than a single networking data link model, that would perform, if we did that, it would perform better today, but would perform worse tomorrow because we can't upgrade in isolation. IP is also very hard to upgrade for the very same reasons. So how long have we been trying to upgrade from IPv4 to IPv6?
Decade.
I think it's since 1998, so I think it's almost 20 years. 2 decades we've been trying to upgrade. Right? And everybody still uses NAT. Right? So, but it did provide for the upgrading and isolation. People can experiment and put new products on the market. So you can have Wi-Fi and you can have power line adapters, all sorts of weird technologies that work on the data link layer and still can communicate with something that's radically different on the other side because they all have IP in common. So it provides that. But in doing so, because we're going to have internetworking, if you're going to communicate with something that on the other side, then and you have to go through something very poor, then your quality service, your bandwidth, whatever, becomes very poor, right? You can't magically stuff more bits across that very poor link, and so it always becomes the lowest link in the chain. So if you have to go to a satellite for some reason and come back down, your latency increases, right? And there's nothing anybody can do about that. So let's take a look.
In the IP world, can't you force a path in an alternate path to that? Like through KPE or I don't know. I always thought this.
So when we get into like the border gateway protocol, you'll see how like paths are chosen. And a lot of times for so we're gonna design a way where it just works. But there'll be problems with it. And then we'll design a way that's going to work better, but it doesn't scale. And then we'll figure out whether we can kind of mesh all those together and come up with a way for it to work and scale. And as we do that, we'll talk about border gateway protocol and how those actually are chosen. How do you choose the path? Right? And it's usually your ISP that's choosing the path. Right, so yes, you can choose a path so long as you have paid money to an ISP to choose that path.
It's all money.
It's always money. So let's take a look at the we're going to take a look at the IP header to see kind of what that actually looks like and what we're adding. So I've been doing things like this, right? I'm going to be saying like, hey, there's a UDP packet. And then we add this IP header on it. Well, what does that IP header actually look like? So if anybody's ever done any Wireshark and actually looked at it, the IP header has a bunch of information in it. And it's useful to kind of look at what information is in there. Because it gives you an idea of what you're actually getting with IP. It also gives you an idea of what you're not getting with IP. So the first thing is the version. So IP header version, in most cases, is for us, ours is going to be 4, the number 4. The next one is the header. And for those guys that have done like file stuff, this is like the magic number and the tolling. And essentially all of this is the header. It's just the header is prepended with the version first. We're going to talk about this later as differentiated services. And then 32 bits wide. And then we're gonna have an ID, some flags, and offset. And then source, destination.
I think you're missing a line. Isn't it 20 bytes?
Oh yeah, I am missing one. It wouldn't work without our time to live. Check. All right. This is what our header looks like. So we have a version, we have the header, we have differentiated services, a total length, ID, some flags, offset, time to live, protocol, our checksum. We all remember that, what that looks like, right? We did that source address, destination address, optional stuff, and then the data packet. So let's go through and actually talk about what those are and what they do. So, version tells us what?
4 or 6.
It's going to be 4 or 6. This is IP, and it tells us what our header size is, what our header structure actually looks like. Right? When we get to IP version 6, actually the header in IP version 6 is simpler, not more complicated than IP version 4. So, total length tells us what?
How long the entire payload is?
It's how long the entire packet is from the IP's perspective. So, hey, you're at IP. Remember, so UDP, IP is not going to exist in isolation, right? Other than on the stack when it's being built. Right? We have our UDP, and then IP, and then some kind of data link layer, which often it looks like this, right? So IP would be this. So that total length would be that. IP has zero idea on what data link layer it's on, right? So the total length is the total length of the IP portion of the packet. But that also includes the header. And we need that because the IP has an optional header space in there where you can stick more information in. So we all remember what the checksum is. What's time to live?
How long the packet stays in the network before it's started?
Yes, how long the network stays in the network. And so it's called time to live, but it's really kind of hops to live. So it is how many hops it gets to stay in the network before the packet dies. What happens when the packet dies, by the way? Time to live expires.
Does the source get a notification?
It does. So the protocol design specifies that if a packet is to be discarded because of time to live has expired, then an ICMP packet is sent back to source. So it reads the source address out, and then it sends a, hey, your time to live expired, back. How could we take advantage of that?
Set the time to live on someone's computer to 1.
So what would happen in our network that we had drawn over to the other side that it inconveniently erased? If we set it to 1, what happens?
Just go to your default gateway back.
Yeah, you make it to your, in a real live scenario, if you set a packet to time to live to 1, it would die at the access point, right? And you get an ICMP back. And if you set it to 2,
1 hop next.
it would probably make it to the first router, right? And then you get an ICMP back. And then if you set it to 3,
Trace route.
yeah, it is traceroute. Traceroute works by setting the time to live, and figuring out getting to hops until you get back. Now, some routers aren't nice. And so if you ever ran a trace route, if you like jump on your computer and you run a trace route to Google right now, there'll be it'll print out a bunch of information and then pause for a while and then print more information out, right? That's because those routers are not sending back ICMPs. They're dying and just discarding the packet. And then protocol. Protocol inside an ICM or inside an IP packet is what? What is that? When it says protocol, is it talking about IP?
TCP, UDP.
Correct. It is talking about the transport layer protocol that is inside of the packet. Why would we put the transport layer protocol inside of the network protocol header?
Gotta know what's coming next.
You gotta know what's coming next. What stack do I pass it to? Right? Do I pass it to TCP or do I pass it to UDP? Right? Or is it an ICMP packet? Right? So what stack do I pass it to? Otherwise, you're going to have to like do some like deep packet analysis trying to figure out what to do with this packet and how to do it. You know, especially if you're on the like server side and this is the packet that comes to you. Right? So there's no established connection, so you can't say, oh, it came from blah blah blah, so this is TCP packet because we had a TCP connection set up. Right? So protocol tells you that. What else? Source address, destination address are pretty self-explanatory, right? We've been talking about those. And we'll talk about differentiated services later. Oh, and the flags. What flags would actually be interesting inside an IP packet?
Quality.
Yeah. It's actually in differentiated services, but what other things? It's a flag, so it's 1 bit. So what things would we want to see?
Broken up or not.
Oh yes, yeah. All right, you've looked at packets, right? Whether we're going to fragment this thing or not, and whether we're going to allow fragmenting or not. So 2 of the most important flags in there are fragmentation flags. One is don't fragment, and the other one is it fragmented. So remember, if we broke up from one data link layer, so Ethernet packet came in at 1500 bytes, and then it went across a PPP link in MTLS and gets broken up into 900 bytes, right? The routers need to know, hey, is this packet that I just got whole, or do I need to reassemble it to send it across, right? And then inside, and that's for a virtual circuit that would reassemble it. Inside a datagram model, they're not going to reassemble it, but the host, when it receives the packet, needs to know, if I need to reassemble it. This packet is not whole. I need to reassemble it before I pass it to the next layer. And so there's flags for that.
When they actually, like, when you fragment a packet, do you have to, like, prepend the IP?
Correct. Yes.
Fragment, okay.
Yeah, you got to build an entire. You got to take a copy of the header and append it to it. But there are some things you're going to need to change in there. One is this, right here, offset. So if the flag is set, the flag that this thing is fragmented is set, then offset will tell you where this thing actually gets put together at. So we have a total length and we have an offset, then we now can, with that, just that information, we can reassemble the packet. So long as that we know that the flag's been set. And we just, it's a way to have, like, if you think of it from a computer science perspective, it's a simple check, right? Is fragmented, and then it's a Boolean value, one way or the other. Then if it is, then send things off to get reassembled.
Are there any flags for like framing like that?
So, but the framing would be in the data link layer. And yes, those do have flags, but that for framing is data link layer. So and by the way, frames are very, very similar to packets because they are differentiated boundaries of data, and both of them contain addresses, right? But a frame delineates a bounded part data at the data link layer, and then a packet is a bounded piece of information at the network layer. So in this, right, the frame is here, and the packet is here. All right. So next class we're going to talk about IP addressing, which is going to take longer than the 8 minutes that we have left. Any questions? I feel like I'm throwing information at you guys very fast, right? But thankfully we're past most of the electrical engineering parts. So now most of us are more comfortable with algorithms. Okay. That's it.
We're going to discuss why